Most development teams are currently trapped in a waiting game, holding out for a mythical perfect flagship model like a hypothetical Opus 5 or GPT-6 to solve their most complex reasoning problems. They operate under the assumption that a bigger model always equals production code. However, the release of Claude 3.5 Sonnet shattered this hierarchy completely. We are witnessing a massive disruption where a mid-tier model is not just competing with, but actively decimating the performance of previous flagships in specialized coding benchmarks and tool use scenarios. In many internal tests, Sonnet 5 achieves superior logic reasoning at only 20% to 30% of the cost of older legacy flagships. This performance paradox creates a dangerous trap. If you continue to default to the largest model for your enterprise agents, you are likely overpaying for higher latency and inferior output. This lecture will dismantle the myth of the flagship and provide you with a cold, data-driven framework for model selection in the 2026 landscape. By the end of this session, you will understand why your current AI architecture is likely burning budget unnecessarily. This looks like a simple upgrade on paper, but in actual production code, it reveals a fundamental flaw in how we perceive AI intelligence. In the fast-moving AI ecosystem of 2026, being a good developer is no longer enough. You must become an economic intelligence engineer. The goal of our new decision framework is not to find the smartest model in a vacuum, but to calculate the threshold of sufficiency for every specific task. We must evaluate three critical pillars: cost-to-token ratio, context window utilization, and agentic reliability. Many engineers fall into the soda trap, blindly chasing the latest state-of-the-art benchmark without considering if their task actually requires that level of reasoning. For example, using a top-tier reasoning model for simple JSON extraction is an architectural failure. We need to build a system that knows when to stay with a stable legacy model and when the agentic leap of a new model, like Sonnet 5, justifies the migration effort. It is about maximizing ROI, not just chasing leaderboards. This framework will serve as your compass in an era where model updates happen monthly rather than yearly. But how did we get here? To understand the current chaos, we have to look at how the very definition of a model tier has shifted over the last 2 years. If we look back at the history of LLMs, we can see a distinct generational shift. Between 2023 and 2024, we lived in the intelligence-first era, where the primary goal was raw knowledge and creative writing capability. Models were evaluated like static encyclopedias. However, as we approach 2026, we have transitioned into the agent-first era. In this new paradigm, a model's value is measured by its ability to reliably call tools, handle massive system prompts without losing instruction-following capability, and maintain state over long iterative loops. Sonnet 5 is the quintessential agent-first model. It is optimized not just to know things, but to do things within a terminal or a browser environment. This evolution means the old vertical hierarchy of large, medium, and small is collapsing into a horizontal ecosystem of specialized capabilities. If your architecture is still built on the 2023 assumption that bigger is smarter, you are architecting for a past that no longer exists in the world of autonomous agents. The traditional hierarchy is dead, and the new data proves that the middle child is now the head of the household. Let's look at the cold hard numbers that define this new reality. In the traditional tier system, the Opus class was the undisputed king of complex reasoning, while Sonnet was the reliable workhorse for mid-range tasks. Today, the lines are completely blurred. In recent coding benchmarks like HumanEval and SWE-Bench, Sonnet 5 achieves a higher success rate than the older flagship models, yet it retains the aggressive pricing structure of a mid-tier model. This creates a massive efficiency delta. For any enterprise team, migrating from a legacy flagship to a modern mid-tier like Sonnet 5 can result in a 70% reduction in total API costs, while simultaneously increasing the speed of the agent's feedback loop. We are no longer looking at a ladder of intelligence. We are looking at a specialized toolbox where the mid-tier is the most versatile instrument. The decision to use Sonnet 5 over a flagship is now a strategic business move, not just a technical preference. Understanding this tiered disruption is the first step in mastering modern AI implementation. Now that we've broken the illusion of the perfect model, it's time to dive into the numbers that actually drive the boardroom, the economics of intelligence. By 2026, the cost of intelligence has plummeted, yet most teams are overspending because they choose models based on hype rather than unit economics. Let's look at the raw numbers. Sonnet 5 positions itself in the Goldilocks zone, delivering GPT-5 class reasoning at a fraction of the cost. While frontier models like GPT-5 might charge a premium for their extreme edge cases, Sonnet 5 targets the high-volume API market. For 1 million tokens of input, we are seeing a shift where the cost-performance curve finally flattens. If you are running a simple array pipeline, using a frontier model is like using a Ferrari to deliver groceries. Open source models like Llama 4 are catching up, but the hidden costs of self-hosting often outweigh the API savings. You need to calculate the total cost of ownership, including the engineering hours spent on fine-tuning. But price per token is no longer the only metric that matters. There's a hidden feature in the API that can slash these bills by another 90%, and it changes everything for long context apps. That hidden feature is prompt catching. In the 2026 landscape, stateful interactions are the norm. When you're building an agent that reads a 200K token codebase, resending that context every time is financial suicide. Anthropic's prompt catching mechanism allows you to freeze a massive prefix and pay only for the incremental delta. This shifts the break-even point for high-context applications significantly. Instead of worrying about every input token, you can now afford to provide the model with massive, detailed documentation or entire code repositories. This architectural shift means the context as a service model is finally viable for production. However, this catching isn't a silver bullet. It requires a specific prompt structure to be effective. If your prompt is dynamic at the beginning, you lose all benefits. It's about engineering your workflow to maximize catch hits. But even with caching, there is one regional factor that Korean developers often ignore, leading to unexpected 30% overheads. This factor is tokenization efficiency, often called the Korean tax. Historically, LLMs used tokenizers optimized for English, meaning a single Korean word could take up 3 to 4 tokens, compared to 1 for English. By 2026, Sonnet 5 has refined its tokenizer to handle CJKK Chinese, Japanese, and Korean much more efficiently. We are seeing a reduction in the token-to-word ratio, which directly impacts your bottom line. When comparing models, you shouldn't just look at the price per 1K tokens. You must look at the price per information unit in your target language. In my experience auditing enterprise AI deployments, switching to a model with a better Korean tokenizer saved more money than switching to a cheaper, dumber model. This efficiency isn't just about cost. It also affects the effective context window size. If your model sees Korean more densely, it can essentially read more content in the same 200K limit. Efficiency is great, but in a production environment, users don't care about your build, they care about speed, which brings us to latency. Let's talk about the time to first token, or TTFT. In 2026, raw intelligence is a commodity, but low latency intelligence is a luxury. Sonnet 5 is engineered for throughput. When we benchmark it across different providers like AWS Bedrock and Anthropic's own VPC, we see significant variance. On average, Sonnet 5 delivers a TFT of under 200 milliseconds for small prompts, making it feel instantaneous. But as your prompt grows, especially when utilizing that 200K context, latency starts to creep up. It's crucial to understand that throughput, tokens per second, and latency, initial response time, are two different beasts. For agentic workflows where the model needs to think in loops, every millisecond of latency compounds. If an agent takes 10 steps to solve a task, a 1-second delay per step adds 10 seconds to the total user wait time. This is where Sonnet 5's balanced architecture beats the heavy frontier models. But how does this raw speed translate to the actual user experience in a real-time streaming application? The perceived speed of an AI application is often more important than the actual completion time. When you use tools like Claude Code or high-performance IDE extensions, the streaming UX is what makes the AI feel like a pair programmer rather than a slow search engine. Sonnet 5's high throughput allows for a fluid, human-like typing speed that keeps users in the flow state. Compare this to heavier models that might pause for 3 seconds to think before dumping a wall of text. Even if the total time is the same, the stutter in heavy models breaks the user's concentration. From an engineering perspective, implementing robust streaming with server-sent events or WebSockets is mandatory to exploit this speed. We are moving away from request-response cycles toward continuous thought streams. If your UI isn't optimized for this, you're wasting the model's potential. Speed is addictive, and once your user experience Sonnet-level responsiveness, they won't go back to anything slower. However, as your user base grows from 10 to 10,000, you'll hit a wall that no amount of code optimization can fix: the rate limit. Rate limits are the silent killers of scaling AI startups. Many developers assume that as long as they have the budget, they can scale indefinitely. In reality, provider-side rate limits on Tier 1 models like Sonnet 5 are still a major bottleneck in 2026. You need to design your architecture for multi-region failover and model fallback from day one. If you hit a rate limit on the primary API, your system should gracefully switch to a secondary provider or a slightly smaller model like Haiku 5 to maintain service. It's also important to distinguish between requests per minute, tokens per minute. High-context agents will hit the token limit long before they hit the request limit. Savvy teams use a token bucket algorithm on their own middleware to throttle non-essential tasks. Scalability in the age of AI isn't just about horizontal pod autoscaling, it's about managing your intelligence quota across your entire fleet of agents. Now that we've mastered the economics and performance of individual calls, it's time to see what happens when we let the model take the wheel in an agentic loop. In the fast-moving landscape of 2026, the true value of a model isn't just how well it chats, but how effectively it acts. This is the core of the agentic shift. Sonnet 5 has emerged as a frontrunner not because it has the highest parameter count, but because of its surgical precision in tool selection. In professional environments, an agentic model must understand the specific schema of a tool and decide with high reliability exactly when and how to invoke it. Most models struggle with overcalling or misinterpreting complex parameters, but Sonnet 5 demonstrates a level of restraint and accuracy that makes it production-ready. This reliability allows developers to trust the model with autonomous tasks that go far beyond simple text generation, forming the backbone of modern AI workflows. But why do models with higher general reasoning scores often fail when given more than 3 or 4 tools? Let's look at the breaking point where Sonnet 5 maintains its composure. Let's get technical. A common failure point in agentic systems is JSON drift, where a model begins to output slightly malformed structures under heavy cognitive load. Imagine a multi-tool workflow where the agent must first fetch a user's logs, parse a specific error code, and then hit a documentation API to find a fix. Sonnet 5 excels here because of its rigorous instruction tuning on function calling. In this code example, notice how the model handles a complex nested-to-JSON response. While other models might fail to escape characters correctly or miss a required field in the second hop, Sonnet 5 maintains structural integrity. This allows for agentic chains where the output of one tool becomes the perfectly formatted input for the next. This isn't just a minor improvement. It's the difference between a broken script and a self-healing automation. However, if the model can handle a single chain, can it actually manage an entire codebase? We're about to dive into repository-wide refactoring and how agents navigate complex structures. The most impressive application of this agentic edge is seen in tools like Claude Code. We are moving beyond the copilot era of autocomplete into the era of AI engineers. These agents don't just suggest a line of code, they reason across the entire repository. When you ask to refactor a global state management system, Sonnet 5 doesn't just look at the open file. It scans the directory, maps out dependencies, runs the shell to check for existing tests, and then iteratively applies changes. This process involves a high-stakes loop: propose, execute, verify, and fix. The stability of Sonnet 5 in this loop is what sets it apart. It can handle long-running processes without losing the context of the initial goal, which is a common failure mode for less agentic models. It effectively turns the IDE into an autonomous workspace. But tools and loops are only half the battle. What happens when the model makes a mistake mid-process? Let's explore the reasoning loops that allow for self-correction. The true test of an agent is how it handles failure. Traditional automation breaks when an API returns an error, but Sonnet 5 uses an internal chain of thought to navigate these hurdles. When a tool call fails, perhaps due to a changed endpoint or an unexpected data format, the model doesn't simply give up or repeat the same error. Instead, it enters a self-correction phase. It analyzes the error message, hypothesizes what went wrong, and adjusts its next tool call accordingly. This metacognitive ability is what reduces the need for human babysitting. In a comparison of agentic models, Sonnet 5 consistently shows a higher recovery rate, the ability to reach the correct goal after an initial failure. It treats errors not as a stop sign, but as a new piece of data to refine its plan. Even with this great reasoning, hallucinations can still be a silent killer in technical tasks. Just how grounded is Sonnet 5 in actual technical reality? Grounding is the anchor of reliability. In professional software engineering, a hallucinated library version or an imaginary API parameter isn't just a mistake, it's a liability that costs developer time. Sonnet 5 has been specifically tuned to prioritize technical grounding. When it's unsure, it is more likely to use a search or read file tool rather than guessing based on its training data. This groundedness is critical for tasks like writing technical documentation or migration guides where accuracy is non-negotiable. Research indicates that Sonnet 5 has significantly lower unforced hallucination rates in technical contexts compared to previous iterations. It treats documentation as a primary source of truth. However, every model has a ceiling, even one as grounded as this. Where does Sonnet 5 finally reach its limits in terms of pure logic? We'll examine the benchmarks to find out. To make an informed decision for 2026, we have to look at the hard data across logic benchmarks like GPQA and MMLU. Sonnet 5 is a powerhouse, often outperforming much larger models in coding and practical reasoning. However, it is not omnipotent. When we push into extremely abstract graduate-level mathematics or ultra-complex logical puzzles that require deep, multi-step symbolic reasoning, Sonnet 5 can reach its ceiling. Sonnet trap occurs when developers assume it can solve PhD-level physics with the same ease it handles a React component. In this table, you can see where it dominates specifically in human-level and MVPP, and where the gap with frontier models still exists. Knowing these limits allows you to build smarter. Use Sonnet 5 for the heavy lifting, but know when to route the most complex logic to a specialized frontier model. We've mastered the agentic flow, but there's a sleeping giant waiting to break your budget, the context window reality, which we'll tackle in the next chapter. Most developers treat the 200K context window as a bottomless bucket, but in professional production, size is secondary to recall. Claude Sonnet 5 might accept a massive codebase, but can it actually find the needle in the haystack when you're 150,000 tokens deep? We often see models hallucinate or default to general knowledge when the specific logic is buried in the middle of a massive file. Effective recall is about how the attention mechanism prioritizes specific tokens across the sequence lengths. If your model has 200K capacity, but only 80% to recall at the 100K mark, your agentic workflows will fail silently, leading to bugs that are nearly impossible to track in automated pipelines. Understanding the difference between theoretical capacity and actual retrieval accuracy is the first step in avoiding the long context trap that wastes both your time and your API credits. However, there is a specific pattern to how these errors occur. It isn't random at all. In the industry, we talk about the lost in the middle phenomenon, where LLMs perform significantly better on information placed at the very beginning or the very end of a prompt. Sonnet 5 attempts to solve this with a more uniform attention distribution, but real-world benchmarks show that data density still matters. When we compare Sonnet 5 to other frontier models at the 128K or 200K threshold, we look for a flat recall curve. If you are building a legal tech agent or a code reviewer, placing your system instructions at the end of a long context can sometimes yield better adherence than placing them at the start. You must monitor the data density. If your context is 90% to filler text and 10% to critical logic, the model might optimize for the noise instead of the signal. This becomes a critical decision point when deciding how to structure your multi-file prompts for Claude Code or custom agents. But wait, there is a point where even a perfect context window becomes a financial liability compared to other architectures. The biggest architectural debate in 2026. Should I use RAG or just dump it all into the context window? With Sonnet 5's massive window and high reasoning capabilities, it's tempting to stop using vector databases entirely. However, we must consider the token churn cost. Every time you send 200K tokens, you are paying for the full input, even if only 1K tokens changed. RAG, Retrieval Augmented Generation, remains superior for massive, static datasets where you only need a few snippets to answer a query. Conversely, long context is unbeatable for tasks requiring global understanding, like refactor this entire repository to use a new library. If your task requires connecting dots between file A and file Z, RAG will likely fail because it only sees fragments. I suggest a hybrid approach. Use RAG to filter down to the most relevant 50K tokens, then let Sonnet 5's reasoning engine handle the rest. This strategy balances cost with the global reasoning that agents require. Now, let's shift our focus to a dimension where context isn't just about size, but about the nuances of the Korean language. When deploying agents in a Korean business environment, Sonnet 5 demonstrates a sophisticated grasp of honorifics and technical jargon, but it isn't flawless. In Korean, the relationship between the speaker and the listener is embedded in the verb endings, what we call jondemo. A common failure in LLM-driven agents is switching between formal and polite styles inconsistently, which can alienate professional users. Sonnet 5's training data includes a vast amount of multilingual technical documentation, making it excellent at translating English documentation into Korean while preserving the correct technical nuance. However, developers must be careful with Konglish terms that might have specific localized meanings in a dev environment versus a general context. Using the right system prompts to enforce a specific tone and manner is essential for enterprise-grade Korean applications. But how do we actually verify if the model is being culturally accurate in an automated way? Verifying Korean output quality requires a specialized checklist, especially when agents are running autonomously. We often see translation hallucinations where the model uses a grammatically correct Korean sentence that makes zero sense in a local business culture. For instance, an agent might translate "let's kill this process" too literally, which sounds aggressive in Korean. You need to check for josa particles, errors that often crop up when the model is trying to reason through complex logic in Korean. I recommend a multi-stage validation, first a grammar check, then a cultural nuance check using a smaller, specialized prompt. If your agent is interacting with Korean clients, you must ensure it doesn't default to a robotic, translation-y style. This checklist will serve as your primary defense against embarrassing localization failures. Up next, we look at the hard numbers. How does Sonnet 5 actually stack up in technical translation benchmarks? As we close this reality check, let's summarize the benchmarks. Sonnet 5 is currently a top-tier model for English to Korean technical translation, specifically for developer documentation like React, Rust, or Kubernetes. Its ability to maintain a contextual terminology map, meaning it remembers that state should be translated as hangtae consistently throughout a 50-page document, is its greatest strength. While purely Korean native models might have a slight edge in deep cultural slang, Sonnet 5 wins on the integration of logic and language. For the 2026 developer, the strategy is clear. Use Sonnet 5 for the heavy lifting of technical Korean context, but maintain a lightweight validation layer. We've covered the now of context and language. It's time to look ahead. In the next chapter, we will take everything we've learned about cost, agents, and context to build a blueprint for the future, architecting for 2026. In the fast-moving landscape of 2026, using a single model for every request is an architectural failure. Even with Claude 5's impressive capabilities, routing every hello or simple data extraction to a high-tier model wastes budget and increases latency. Instead, modern production stacks utilize a router layer. This layer acts as an intelligent traffic controller, using semantic routing to analyze intent before the main execution. Simple tasks like greeting or basic formatting are offloaded to lightweight models like Haiku, while complex reasoning, agentic tool use, and long context synthesis are reserved for Sonnet 5. This hybrid approach ensures you are maximizing the ROI of every token spent. By implementing an embedding-based classifier or a high-speed prompt-based router, you can reduce cost by up to 40% without sacrificing the smart feel of your application. But what happens when your smart router or the primary model itself encounters a hurdle? The next scene reveals how to build a resilient safety net. Reliability in 2026 isn't just about uptime, it's about handling the nuances of AI failures. Sonnet 5 is powerful, but is not immune to rate limits, safety filter refusals, or occasional API latency spikes. A robust architecture must implement a fallback logic process. When a request to Sonnet 5 fails or triggers a safety refusal, the system should automatically retry or pivot to a secondary model like GPT-4o Mini or a local Llama instance. We call this a multi-provider circuit breaker. Furthermore, for agentic workflows where Sonnet 5 might get stuck in a loop, your system needs monitoring to detect stall states and force a context reset. This prevents your API costs from spiraling out of control due to an agent's infinite retry loop. If you ignore these reliability patterns, your application will feel broken the moment Anthropic's servers face heavy load. Once you have the routing and fallback ready, how do you actually move your existing code over? Let's look at the migration checklist. Migrating to Sonnet 5 from GPT-4 or Claude 3.0 isn't a simple search and replace of the API key. In my experience with high-scale deployments, the biggest hurdle is prompt drift. Claude models respond exceptionally well to XML tags using structures like boda tagen instructions, boda kun, and boda tagen context, boda kun, whereas GPT models are often optimized for Markdown. Your first step must be a system prompt audit. You need to refactor instructions to leverage Sonnet 5's improved tool calling reliability. Second, validate your JSON output schemas. Sonnet 5 is stricter. If your schema is ambiguous, it might hallucinate keys. Third, test the context recall. Just because the window is large doesn't mean the model sees everything equally. Use a needle in a haystack test for your specific document types before going live. This 5-step checklist is the difference between a smooth launch and a week of emergency hotfixes. This approach sounds thorough, but is it enough to survive the next model release? Let's talk about future-proofing your entire AI strategy. To thrive in 2026, you must remain model agnostic even while taking full advantage of Sonnet 5's current dominance. Technology landscape is too volatile for hard-coded dependencies. The key is to build an abstraction layer and AI gateway that separates your business logic from the specific API quirks of any one provider. Treat prompts as code. Store them in version-controlled repositories rather than burying them in your backend scripts. By utilizing standardized benchmarks and evaluation frameworks like G-Evil or RAGAS, you can objectively determine when the next Model X surpasses Sonnet 5 and switch with minimal friction. This architectural decoupling is your insurance policy against vendor lock-in and pricing spikes. We have covered the routing, the reliability, and the migration. Now it's time for the hard truth. Does Sonnet 5 actually live up to the hype for your specific business case? In the next and final chapter, we will deliver the final judgment on whether you should go all in or wait for the next wave. As we conclude this deep dive, we must face the reality of the 2026 AI landscape. Choosing a model like Claude Sonnet 5 is no longer just about performance benchmarks. It is a strategic architectural decision based on the agentic ROI. This table provides the 3-axis framework you need to apply today. Sonnet 5 stands as the undisputed champion for high-frequency agentic tasks where tool calling speed and a massive 200K context window are critical for maintaining state. However, the trap lies in using it for everything. For high-stakes logical reasoning or zero-shot complex architectural design, the Opus class models still hold a slim but vital margin in reliability. Meanwhile, local models have matured to handle sub-10B parameter tasks with near-zero latency for edge case filtering. If your project demands 99.9% data privacy or millisecond responses for simple classification, going local is the only rational move. The key is to stop looking for the best model and start mapping your specific workloads to this 2026 matrix to avoid overpaying for intelligence you don't actually use. But wait, even with the right model, most teams are still building in a way that is doomed to fail. My final judgment is this: the Sonnet 5 trap isn't just about the model, it is the mindset of building wrappers instead of ecosystems. In 2026, the model is a commodity, a replaceable CPU in a much larger machine. If your value proposition is simply use the latest Claude model, you have no moat. To stay ahead, you must build for multi-model orchestration. Use Sonnet 5 for the heavy lifting of agentic tool use loops, but ensure your architecture allows for a seamless failover to local models or a step up to higher reasoning tiers. Focus your engineering efforts on your proprietary context, your vector databases, your unique toolsets, and your evaluation pipelines. The developers who win will be those who treat the LLM as an interchangeable component. We are moving from the era of AI chat to the era of agentic operating systems. Don't just implement Sonnet 5. Architect a system where Sonnet 5 is merely the first of many engines you will utilize. This concludes our deep dive into the Sonnet 5 trap. It is time to stop testing prompts and start building resilient, model-agnostic agentic infrastructure that survives the rapid cycles of the AI industry. Now that you have the framework, the final question is, are you ready to stop chasing the hype and start building for 2026?